So the problem states that an electron is confined within a one-dimensional infinite potential well of width L is equals to 0.80 nanometers. So we are asked to calculate the ground state energy eigenvalue e to the 1 of this particle in electron volts. So we're going to take the values here according to what the question requires. We have H is equals to 6.63 times 10 to the negative 34 joule seconds. And we have the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. And a conversion where 1 electron volts is equivalent to 1.60 times 10 to the negative 19 joules of energy. So an infinite potential well of width L has a potential energy of 0 inside the region where 0 is lesser than x, but this x is also lesser than L. In other words, 0 lesser than x lesser than L. And everywhere else inside this region will be infinite. In other words, the potential will be infinite. So inside this infinite potential well, we have this time-independent Schrödinger equation. So we have this negative h bar squared all over Tm times the second derivative of the wave function with respect to x, or position, if I'm not wrong, and then E, which is energy, times the wave function. Alright, so because the potential energy is infinite outside this well, the electron cannot exist there. So we need the wave function to drop to 0 at the walls of this infinite potential well. In other words, we have an initial value to our differential equation where psi of 0 is equals to 0 and psi of L is equals to 0. This is our initial values, initial conditions. So let's define this as k squared. We're going to have a very nice differential equation. So now we have this right here. And now we can go ahead and solve the differential equation. And me personally, I would like to solve this differential equation using infinite series. So let's begin. So we have found the analytical solution to the differential equation. But, of course, this is still not complete, because we did had a initial condition. So remember that we did say that psi of 0 must equals to 0. And psi of this width L must also equals to 0. Okay, so let's go ahead and plug in our solution. So we have psi of 0, which is equals to a cosine of 0 plus b sine of 0. And since cosine of 0 is 1 and sine of 0 is 0, this is going to cancel out because it's just 0. And a will remain. So therefore, a will be this. Psi of 0 will be a. In other words, psi of a will also equals to 0. I mean, psi of 0 is equal to a, which is also equals to 0. Now, this will simplify our wave function, which is going to be psi of x, which will equals to b sine of kx. because now next we will evaluate if x becomes psi of L. And we did mention that a sine of KL will must equals to 0. So to avoid a trivial solution, we need to avoid this trivial solution where a is equals to 0, because that means there is no electron. So the sine function itself must be 0. This will only occur if the argument itself is an integer multiple of pi. So we have to write this. K of L, K times L, is equals to n times pi. If we were to solve for the constant K, let's just go ahead and divide both sides of the equation by L. And we're going to have K is equals to n pi all over L. Now you may be wondering, what happened to the sign though? Because here in our initial condition, we already said that a is equals to 0. And since 0 times the cosine of k of x is 0, then we only need to worry about this wave function right here. So in this expression, n is the principal quantum number. We all know this, which is 1, 2, 3, and so on. So here, from here on now, we can go ahead and extract the energy eigenvalue. So let's square both sides. But wait, we did also mention that k squared is equals to 2m times the energy all over the reduced Planck's constant squared. So we need to focus on this, E. Okay, so let's go ahead and solve for this new equation, which is n squared times times pi squared all over L squared, and that's equals to 2m all over h bar squared times E. So we have to multiply both sides of the equation by the inverse of this term, which is, again, we return to from the original Schrödinger equation, which is this. So these cancels out. Okay, so now we can go ahead and multiply here, this entire term here beside this fraction. So finally, we will have the energy eigenvalue, which is n squared times pi squared times the reduced Planck's constant squared all over 2m times L squared. And remember, L is our width. Okay, so the ground state energy. Okay, let's check at the problem again. We are asked to calculate the ground state energy eigenvalue e to the 1 of this particle in electron volts. So what we are going to do is we're going to set n is equals to 1. Okay, so e to the 1 is equals to pi squared times h bar squared all over 2m times L squared. We were given that the Planck constant is 6.63 times 10 to the negative 34 joule seconds. This is the reduced Planck's constant. So we need to use the identity for the reduced Planck's constant. So as we all know, h bar is equals to h all over 2 pi. The reduced Planck's constant is the whole Planck's constant divided by 2 pi. So we're going to substitute that in our equation. So we have pi squared all over h all over 2 pi and then squared. Square that and all over 2m times L squared. So we need to move this down so it doesn't become too vague. So we have e to the 1 equals pi squared all over 2m L squared times h squared all over 2 pi. Oops, we forgot to square the denominator. Sorry. So we have 4 pi squared. And surprisingly, the pi squares cancels out, leaving us with 4 multiplying 2. So therefore, we have h squared all over 8ml squared. And then, the mass, well, that's just going to be 8 times the mass of the electron times our width. Okay, so let us substitute the values of the given 6.63 times 10 times 10 to the negative 34 joules second squared all over 8 times the mass. I have to use the calculator for this one. I'm using my calculator, and we have 9.42 times 10 to the negative 20 joules. Alright. So we need to convert this to electrovolts, yes? So we have 0.589 electrovolts. So that is our answer. If you enjoyed this video, please like and subscribe.